In this podcast, we're going to talk about average atomic mass, specifically how to calculate it. All right, so first let's remind ourselves about atomic mass. Atomic mass is when you determine the average of all the naturally occurring isotopes of an element. So here we have a chart, and it has all the isotopes of carbon. So we have carbon 12, 13, and 14. And remember, what makes something an isotope is that it has a different number of neutrons, which affects its mass number. And then we have over here their percent abundances. That's how often we find them in nature. So just by looking at this, we can see that the average mass of carbon is 12.011. Now, why is it close to 12? Well, the reason it's close to 12 is because 98%, or almost 99%, of the carbon you would find in nature would be carbon 12. Okay, so to estimate the average atomic mass, all you do is look for the element with the highest percent abundance, and that'll be the mass that the average is closest to. Okay, so we have the most carbon 12, which is why our mass of carbon is very close to 12. All right, now how do we calculate average atomic mass? Well, what you want to do is you want to multiply the mass of each isotope by the percent abundance. Now, the percent abundance needs to be in decimal form. Then you're going to line all those up, and then you're going to add them, and that'll be your answer. So you take your mass of the first isotope times the percent abundance, mass of second isotope times the percent abundance, and if you have a third isotope, the third times the percent abundance, add them all up, and that gives you your answer. All right, so let's look at an example problem. So in this problem, we have three different isotopes in neon. We have carbon. We have neon 20, 21, and 22. And then we have over here the percent abundances. Then question A is, without calculating, what's the approximate mass of neon? So we want to look at our percent abundances. Well, we have 90.84% of neon 20. So the approximate mass is going to be really close to 20. Okay? Now to calculate the actual atomic mass, you want to do the equation like we were doing on the previous page. So we're going to take the mass of the first isotope, okay, and we're going to multiply it by the percentage in decimal form. So 90.84% is 0.9084. Okay, we're going to get that answer. All right, we're going to multiply it by the mass from the second isotope. So we've got second isotope mass. And then we want to get the percentage into decimal form. All right, and then the third isotope. And we'll multiply that one by the percent abundance. All right, let me work all these out for us real quick. All right, so for the first one, I got 18.16109616, and I'm just writing the full number so that we can make sure that we are getting the correct numbers here. All right, the second one we got 0.0545844. All right, and the last one, we get 1.93572346. All right, we're going to add all those up. All right, and that gives us our average mass at 20 0.1729 AMUs. Okay? Alright, so that's not too bad. Now, what if we were asked to go in reverse? Alright, so in this problem, we have two isotopes of copper, 63 and 65, gives us their masses, wants us to find the percent abundances. Okay, so we have to look at our periodic table to determine the mass, the average mass of copper. So if you look at the periodic table, it should be 63.55. Okay, now we're going to set it up. So we got our first mass. Alright, now we got our percentage. So we're going to call this first percentage just X. Okay, and we're going to add our second one. So I'm going to go ahead and write that up here so we remember we called this one X. Okay, and then we got 64.927793. Alright, and then we got to figure out what we're going to call the percent abundance of this one. Okay, well, remember we're dealing with percent abundances in percentage form, and any of the percentages have to add up to 100, okay? So say we had 70% and 30%. If they were in decimal, they'd be 0.7 and 0.3. So they would have to add up to be 1, okay? So we need our answer to be the difference between 1 and X. Okay, so we're just going to go ahead and plug in 1 minus X right here. Okay, the difference between 1 and X. Right now it's just a math problem, so you got to distribute this in to both of these. Alright, so here we got 64.9279, whoops, there's 777793 minus 64.927793 X. On this side, we still had our X term. Alright, and it's all still equal to 63.55. Alright, now we need to combine like terms. So we have, whoops, we have an X term there, and we have an X term there. So we need to combine those terms. So let me plug that in the calculator. So we got 62.939598 minus 64.927793X. Alright, so that gives us negative 1.988195X. And then we still got this non-X term over here. Okay, and that is all still equal to the 63.55. Now, still want to get our like terms together, so we have a non-X term and a non-X term, so we're going to subtract this on both sides. Alright, so on this side we got 63.55 minus 64.927793. So that gives us negative 1.377793. And that's still equal to our X term over here. Alright. Now, how do we get X by itself? We want to divide by the negative 1.98195, both sides. Alright, cancels out. So, our X is 0.6929, which in percentage would be 69.29%. Okay, and that is, remember, our X term was associated with copper 63. Okay, now, to find the percentage that was copper 65, we simply just subtract from 100, right? So you got 100 minus 69.29, it's 30.71. So you got 30.71% was copper 65 and 69.29% was copper 63.